Here are the objectives that we discussed in our last meeting. We learned how to name acids and bases and introduced Arrhenius acids and bases. In section 2, we defined Bronsted-Lowry acids and bases as proton donors and proton acceptors. In section 3, we wrote equations for the dissociation of strong and weak acids and bases, which are similar to those of strong and weak electrolytes that we learned in chapter 9. For weak acids and bases, we used Le Chatelier's principle to explain changes in equilibrium. And in section 5, we used the dissociation equation of water to calculate the concentration of H+ and OH-. The concentrations of acids are usually very small numbers. To make them more convenient, you can express concentrations as pH. pH is defined as the negative logarithm of the concentration of H3O+. Given any concentration of H3O+, you can determine the pH. For example, if the concentration is 1.0 times 10 to the negative 2, the pH is 2. Note that the number of significant digits in the coefficient of the concentration becomes the number of decimal places in the pH. There are several instruments and methods that are used to measure pH. A pH meter is an electronic device that determines pH very accurately. You can also use a pH indicator paper, which some of you may have used to test the pH in your swimming pools. Lastly, different compounds can act as pH indicators, as their color will change with pH. The pH scale ranges from 1 to 14. Here are some pHs of common substances. If the pH is less than 7.0, the substance is acidic. An example is 1.0 molar HCl, which has a pH of 0.0. And if the pH is 7.0, the substance is neutral. And one example is pure water. If the pH is greater than 7.0, the substance is basic, like lye, sodium hydroxide, which has a pH of 14.0. Note that as the concentration of H3O increases, the pH decreases. Also, a 10-fold increase in concentration corresponds to a decrease in pH by 1. Practice using the dissociation constant equation and the pH equation to practice calculating the quantities in this table. In addition to calculating pH from concentration of H3O+, you can also calculate H3O+ concentration from pH. The concentration of H3O+ is 10 raised to the negative pH. 3 examples are shown here. Make sure you feel comfortable calculating pH given the concentration of H3O+. Acids are very useful substances, and many processes in our bodies rely on reactions of acids. In this section, we will learn some reactions of acids. There are 3 main types of reactions of acids. An acid can react with metals, bicarbonate, carbonates, and bases. When acids react with metals, they produce a salt and hydrogen gas. This reaction is the reason why acids corrode metals, and acid rain can destroy metal structures. Note that in these reactions, the metals are oxidized, while hydrogen ions are reduced. Acids can also react with carbonates and bicarbonates, both weak bases, to produce carbon dioxide, a salt, and water. The fizz that you see when you add Alka-Seltzer to water is carbon dioxide being produced from the reaction of an acid and a bicarbonate. When acids react with strong bases, they produce salt and water. This is called a neutralization reaction because the products generally have a pH that's near neutral. Consider the equation between acid HCl and base sodium hydroxide. Since it's a neutralization reaction, it produces a salt, sodium chloride, and water. From the complete ionic equation, we see that the sodium and the chloride ions remain unchanged and are spectator ions. So the net ionic equation shows that the overall reaction occurs as the H plus from the acid and the OH minus from the base form water. Balancing a neutralization reaction is just like balancing any other reaction. Pause this video and attempt this problem before moving forward. You are given the reagents magnesium hydroxide and nitric acid. You need to write a balanced equation for this reaction. In step 1, write the reactants and products. Since it is a neutralization reaction, it produces salt and water. The H plus from the acid and the OH minus from the base form water, while the remaining ions, magnesium 2 plus and nitrate, form the salt, magnesium nitrate. In step 2, balance the reaction. There are 2 nitrogen atoms on the product side versus 1 on the reactant. To balance, place the coefficient 2 in front of nitric acid. Note that there are 4 hydrogens at the left side and 2 at the right. So you add the coefficient 2 in front of water to balance the hydrogens. Now confirm that all the atoms are now balanced. Neutralization reactions are powerful reactions for determining the concentration or molarity of an acid or base. One laboratory technique used to determine concentration is called titration. You can use titration to determine the volume of a base of known concentration that is needed to react with an acid of known volume but unknown concentration. Based on the balanced molecular equation, you can calculate the concentration of the base. Pause this video and recall what molarity is. In this example of an acid-base titration, sodium hydroxide of known concentration is placed in a burette, while a known volume of an acid with an unknown concentration is placed in an Erlenmeyer flask. A phenolphthalein indicator is added to the acid. Phenolphthalein is colorless in acidic solution and pink in basic solution. At the end point, the moles of base are equal to the moles in the acid solution. The burette gives the volume of the base used to reach the end point, and the molarity of the acid is then calculated using the neutralization equation for the reaction. Here's an example for determining the concentration of an acid using titration. Pause the video and attempt the question before proceeding. The first step is always to determine the information you are given and what you need to find. You have volume and concentration of sodium hydroxide and volume of hydrochloric acid. You need to find the concentration of HCl. In step 2, determine your plan for finding the concentration or molarity of HCl. Molarity relates liters to moles. So first, convert mils of sodium hydroxide to liters of sodium hydroxide. Then use molarity to convert liters of sodium hydroxide to moles of sodium hydroxide. The molecular equation gives the ratio of moles of sodium hydroxide to the moles of HCl. And lastly, use the equation for molarity to convert moles of HCl to molarity of HCl. In step 3, determine the necessary equalities and conversion factors to convert from moles of sodium hydroxide to liters of sodium hydroxide to moles of sodium hydroxide to moles of HCl, and finally molarity of HCl. And lastly, set up your calculation, making sure all the units cancel except moles of HCl over liters of HCl. I cannot emphasize this enough. Unless you keep track of your units, you run the risk of omitting an important conversion factor. So keep track of your units, and after the calculation, always make sure you use the correct significant digits. Acid-base equilibrium enables us to create buffers. Unlike most substances, buffers resist changes in pH when either an acid or a base is added to them. Buffers are crucial in physiological systems where our enzymes operate in a small pH range, which is why our bodies maintain a pH of around 7.4. If you add an acid or base to water, there is a significant change in pH. But if you add an acid or base to a buffer solution, the pH change is very minimal. A buffer is made up of two crucial components: a weak acid and a salt of its conjugate base present in equal amounts. Recall that acid-base conjugate pairs differ by 1 H+. An example of a buffer solution is acetic acid, which is a weak acid, and a salt containing acetate, a conjugate base of acetic acid. Note that acetic acid and acetate differ by only 1 H+. Consult your solubility rules to confirm that sodium acetate is soluble in water. As such, it is a strong electrolyte and will completely dissociate to acetate ion and sodium ion. Acetic acid, being a weak electrolyte, would normally produce a large amount of acetic acid and a small amount of acetate and H3O+. But the addition of sodium acetate ensures that a large amount of acetate is present as well. So if you add a base to an acetic acid acetate buffer, the large amount of acetic acid will consume the base and produce more acetate. As such, the concentration of H3O+ and the pH aren't greatly affected. If on the other hand you add acid, the large amount of acetate will react with the acid to produce acetic acid, so there will not be a great change in the concentration of H3O+ and pH. The most important buffer in your body is the carbonic acid bicarbonate buffer, and it works in the same way as discussed here. We have come to the end of chapter 10, dealing with acids and bases. Use this concept map to identify areas where you need further explanation, and we can discuss this in class. As always, happy studying.